Hey kiddos, Mix there here. Today we're going to be talking about percent error, and your learning target is that I can use a formula to calculate percent error. Ooh. Let's start off with some pieces of vocabulary. And the first piece of vocabulary we're going to look at is this idea of absolute error. And what absolute error is it's a measurement that uses the difference, so subtraction, between an approximate value and an exact value. And this comes up a lot in science classes, especially if you're working with chemistry. It is solved in order to find your absolute error. You will find the absolute value that came up in Unit 1. We'll be practicing this term absolute value a little bit more. You'll find the absolute value of the difference between, again, an approximate value and an exact value. And something that ties into absolute error and that comes up a lot for percent error is this idea of a range of acceptable error. Acceptable meaning this is something that it's within the range of being okay. Mistakes are going to happen. Error is going to exist when we're collecting data. So your range of acceptable error is the space between numbers that still makes a situation okay. So an example of that is if we have an ideal number of students per class is a 25, and then schools say that there's a range of acceptable error of 7, we could say that it would be acceptable to have 32 students because that is our ideal value of 25 plus that range of acceptable error of 7. And we could also go as low as 18 because once again, that is our ideal value of 25 minus that range of acceptable error of 7. And this ties into absolute error because for both of these values, both 18 and 25, the absolute error is 7. And here's some examples below. So in this first example, we have the absolute value of 18 minus 25, which again is our approximate minus our exact value. And that is going to equal the absolute value of negative 7, which just equals 7. And then 32 minus 25, which again is that approximate value minus our exact value, is going to be the absolute value of 7, which again is just 7. Let's look at an example of how to use absolute error. So we're doing a science experiment and it calls for 150 milliliters of water, but Ms. Armgart measures 147 milliliters. What is the absolute error? And what you're going to want to start to do is think, okay, what do we know? What is the approximate value of milliliters? What is the exact value of milliliters? And then we can calculate using A minus V and find out the absolute error of Miss Armgart's measurement. And heading back over to the story, we can see that if an experiment calls for a certain amount, that is going to be your exact value. And then what you actually do, or in this case what Miss Armgart actually does, will be that approximate. And then we can use our formula to calculate that absolute error. So the absolute value of 147 minus 150 is the absolute value of negative 3. And remember, because absolute value means distance from 0, and distance is always a positive, and there's a number line to bring it all the way back to Unit 1, that means that this actual answer is just 3. So your solution would be the absolute error is 3 milliliters. And please don't forget those units. All right, I want you all to try this one on your own. We have Labasse measuring the mass of an object, and he measured it to be 56 grams, but the actual mass is 53. Go ahead and work through this process and calculate the absolute error of the mass of this object. So there's your approximate value of 56, your exact value of 53, and the absolute value of 56 minus 53 equals the absolute value of positive 3, which just equals 3. And your solution is, the absolute error is 3 grams. And again, grams, units. The reason it's helpful to understand how to work with absolute error is because it's really important in calculating a percent of error, which becomes very necessary when we are collecting any kind of data. So an example of when we would want to know our percent error is, like in our last example, if we're calculating the mass of an object in science, or if you want to go into some kind of astronomy and you are measuring the distance of an object has traveled and it's a very large distance, then there's going to be error. We want to be able to say exactly what that error is. So the way that we calculate our percent error is using this equation. And so we'll be looking at, it's very similar to the same proportions we've been looking at, but we have our partial percentage over 100. And then right here, you can see our numerator right here is our absolute error divided by that exact quantity. And so in that last slide, we were talking about these as A and V. And then this would also be V. In this first example, we have all the information we need to calculate this absolute error, and what we're looking for is our percent error. So during a chaotic school assembly, Ms. Trump is trying to take attendance, and she counts 356 students. There were actually 376 students present, and we want to know what was Ms. Trump's percent error. So let's start with what we know. We can find our absolute error. We know our approximate. We know the exact value, so we can say the absolute value of 356 minus 376 is going to give us that absolute error, which is the absolute value of negative 20, which just equals positive 20. And then we're going to need that exact amount, and it might sound redundant, but I'm just going to write it down. That exact amount again was 376. So now we can move into using our percent error formula, because what we are looking for is that partial percentage. We're looking for our percent error. I'll go ahead and highlight that in red. Percent error. All right, let's plug it in with what we know. So we've got x for that unknown percent error over 100 is equal to 20. And I got that 20 from when we did that work with our absolute error up here. So 20 divided by our exact amount of 376. Now I can do either my scaling or my cross multiplication. And using cross multiplication, I came up with 376x is equal to 2,000. Use my inverse operations to divide by 376. And what I get is a pretty wacky decimal. It's 5.319148894. You can go ahead and round that to your nearest tenth, and we can just say that x equals 5.3. But we still need to talk about the solution. What does that number mean? And what all of this work means is that Ms. Trump had a 5.3% error on her attendance. This problem is a little bit different, but it's going to use the same general pattern. So here, our absolute error is our unknown. So we have a socially distanced Blazers game, and there should be 250 seats. There is a percent error of 20% on the count, and this is asking us what is that range of acceptable number of seats. So go ahead and give this a try. Go back to this idea of a range of acceptable error and see what you come up with. And again, what we're solving for is this x, which has been where our absolute error is. But in this case, it's going to mean our range of acceptable error. Go ahead and play around with it. Come back and see how you did. Here's the proportion, how I set it up with my percent error of 20%, my exact amount of 250. I used cross multiplication to solve and came up with x equals 50. So, range of acceptable seats. So if 250 is our ideal, and we have an absolute error of 50, then that range of acceptable error is a maximum of 250 plus 50 seats, or 300 seats and a minimum of 250 seats minus 50 seats, or 200 seats. That would be our range of acceptable error. So putting that in a sentence, the range of acceptable error is between 200 and 300 seats. All right, go ahead and practice your journal problems. Good luck, y'all.